Let's go on. The Arrhenius definition of bases. So a base is a substance that produces hydroxide ions in aqueous solution. Sodium hydroxide is considered an Arrhenius base because it dissociates in water and forms sodium ions and hydroxide ions. So metal hydroxides, sodium hydroxide, lithium hydroxide, potassium hydroxide, it's very easy to see how those form hydroxide ions in solution and how they are Arrhenius bases. But there are a lot of compounds that contain OH groups that are not bases. So methanol, this is the formula for methanol, CH3OH. It's got OH on it. Why isn't it a base? Well, it doesn't ionize. It does not ionize when you put it in solution, and so it's not a base. Using this definition, acids and bases are naturally going to combine to form water. An acid will release hydrogen ions. Bases release hydroxide ions. Well, what do you get if you put a hydroxide ion and a hydrogen ion together? You get water. And you have neutralized the acid and the base because they are no longer releasing hydrogen or hydroxide ions. This definition, though, does not explain why some substances act as bases even though they don't have hydroxide ions. And the Arrhenius definition does not apply when we're talking about non-aqueous solvents. So then there's the Bronsted-Lowry definition, which is more useful and more general. An acid is a proton donor, and a base is a proton acceptor. This definition applies to a much wider range of compounds, and it also works in non-aqueous solutions. So does this contradict the definition, the Arrhenius definition? The Arrhenius definition said an acid was something that released hydrogen ions. What is a hydrogen ion? It's a proton. So the Bronsted-Lowry definition says an acid is something that is a proton donor. It donates protons, which those two statements agree. A base now, instead of something that forms hydroxide ions, is something that accepts protons. Whoops. So bases in the Arrhenius definition produced hydroxide ions. Can hydroxide ions accept protons? Yeah, with this H plus, get it together with that, and it makes water. So hydroxide ions are proton acceptors. But this definition focuses on the transfer of the hydrogen ion or the proton. Hydrogen ion is a proton. They're two different names for exactly the same thing. HCl is a Bronsted-Lowry acid because it donates a proton to the water. So this is really a more accurate definition of what's happening when you put HCl, hydrochloric acid, in water. HCl donates a hydrogen ion to the water, and you get the hydronium ion, and then what's left? The chloride ion. So HCl is the proton donor, and water is the proton acceptor. So that makes water a base. So let's look at something like ammonia. Looking at this formula, NH3, is that going to release hydroxide ions? It doesn't have any oxygen in it. How could it form hydroxide ions? The Arrhenius definition doesn't work on that. And yet, ammonia is a base. What happens is, when you put ammonia in water, the water donates the proton to the NH3, forming NH4. So here the water is the acid, and the NH3 is the proton acceptor. It's accepting the proton, it's acting as the base. Is this making any sense at all?
So is there going to be questions like that, either on the homework or on an exam where it's, is it a Bronsted or Arrhenius?
Mm-mm.
Oh, because
No. I'm telling you these different definitions, but I'm not going to quiz you on their names.
oh,
Because I think that's just, I don't know. Let's focus on the more important things and less on the little names and stuff. But what I might ask you to do is to look at an equation like this and say, is NH3 acting as an acid or a base? And how do you answer that? Well, you look and see, well, what does it do? I could give you this equation and say, is NH3 acting as an acid or a base? Well, what happened to it? It gained H+. It accepted a proton. Therefore, it's a base. And the water here is acting as an acid because it's losing or donating one of its hydrogens to the ammonia. So those are the sorts of questions. Acids and bases always happen together. So proton donors, proton acceptors. You can't donate a proton if there's no one to accept it. So again, the proton's like the baby. You can't pass the baby to someone if there's no one there to take the baby. You can't just set the baby in midair. You can't leave the baby on the table. Not if you don't want to get in trouble. You shouldn't. You really, really shouldn't. So here, HCl, this is an acid, but it can only act as an acid if there's a base to accept the proton. Well, water is the base. But in this situation, where we have ammonia is acting as the base, and now water is acting as the acid. So water's kind of a weird thing. It can act as a base, and it can act as an acid. And something like that, we have a word for it, amphoteric. Amphoteric is a substance, like water, that can act as an acid or a base. It can either accept or donate a proton, depending on the situation. So amphoteric. Where does an amphibian live? Amphibians can live in the water and on the land, right? They can do both, right? An amphibious vehicle can go on land or in the water. So this is a prefix that has a meaning. So amphoteric, it can go both ways. What happens if we switch this equation around? So we're looking at this equation right here, but we're going to just flip it. So now we have the NH4 plus as the reactant and the OH minus as the reactant and the ammonia and the water as the product. So NH4 plus is now becoming NH3. What is it doing? How is it becoming this? It's donating a proton. And who's accepting the proton? The OH minus. So now NH4 plus is acting as the acid and OH minus is acting as the base. And notice that this is an equilibrium. This reaction is going both ways. So we refer to the NH4 plus and the NH3 as a conjugate acid-base pair. They go together. This one acts like an acid, it donates its proton, it becomes this one, but then that one could act like a base and accept a proton, and they could go back and forth all day long. So a conjugate acid-base pair. Two substances that are related by the transfer of a proton. The only difference between them is that one has an H plus and one does not. So these are conjugate acid-base pairs. If you take this one and you add an H plus, you get that one. If you take an H plus off of this one, you get that. Here's another conjugate acid-base pair. H2O, you remove an H plus, you get OH minus. If you take OH minus and you add H plus, you get H2O. The only difference between them is whether they're holding the baby or not. Does that make sense? So in an acid-base reaction, the base accepts the proton, and in doing so, it becomes the conjugate acid. So if I have the baby in my arms and I hand it to my husband, I have donated the baby to him, I've given it to him, I have acted as an acid. He is now acting as the base. So if you're having a hard time remembering, is the base accepting or donating? The base is like the babysitter. Okay, the acid had the baby to start with and gave it to the babysitter. The base is the babysitter who takes the hydrogen ion. So my husband takes the hydrogen ion, takes the baby, and then now he is in a position to be an acid because he could donate, he could give that baby, pass it off to somebody else. He could give it back to me, he could hand it to James, he could let Tommy hold it. You shouldn't give it to Andrew. Anyway, Andrew was the baby. He's just gotten really big. So a base accepts a proton, becoming an acid. The acid donates the proton, in the process becomes a base. So they're very, very related to each other.